So let us start on Friday. We started effectively on Friday, as a quick recap, with this reset and synchronization. Then we did a little bit about the about serial protocols, and then we had a quick look over what is actually needed to build out of what we learned here in the course some processor. And then we started a little bit with the main topic for today, namely addition. Okay, so if we talk about reset, which two different types of reset do we have, and what are the respective benefits and drawbacks? So we have two kinds of basic kinds of resets, right? And the question is, which are those, and what are the benefits and drawbacks of it? Yes, yes. And what is there beneficial, non-beneficial? So you said already asynchronous resets immediately. Yeah. So it's also in safety critical applications where you do not want to rely on the clock, or you have a super slow clock and want to react faster. This is a good fit. What's the benefit of a synchronous reset? Yes. Why is there no invalid state? Yes. And why does this help us to avoid a state where the things are, you're right that this is the effect. You're right that the clock is the reason for that. What I try to ask is, why is the clock the reason for that? So we had this construction here on Friday, that here, right? We had this construction here, and we neglect this part. No? Now we do here all the reset only synchronous, pure synchronous. Huh? The input here is not synchronous. Do we avoid the inconsistent state here? Not really, right? So only making the flip-flops here synchronous is not enough, because we can still, relative to the clock, come to a point in time with our asynchronous reset from extern that causes that our timing for the flip-flops is. So what us actually helps is if we synchronize here and here, because then we can do a good timing calculation, right? So we know that from here to all the flip-flops internally, we have a specific time period, and only after this time period the reset happens. And if we have here synchronized and then distributed the signal, that actually really helps against any metastability issues and so on. So only synchronization, not really, or only up to a certain extent. Okay, then, so if we now compare, effectively the synchronous reset is better in terms of valid set of our internal state. The asynchronous reset is better in terms of a valid reset of our complete system, right? So what we do is we combine the two and we build such a reset synchronizer. So why are there more than one flip-flops? Yeah. Just as we can have with an input in a clock, a root cause for a metastable state, we can have the same with a reset in the clock. So this is effectively why we want to have. Good. Any open questions to this reset synchronization stuff? Good. Then we talked about the serial protocols. So we had three serial protocols discussed. The first one was a UART. The second one was SPI. And the last one was this I2C, right? What are the, well, let's say, specifica of the different protocols? So if we start with UART, what is there different from the other ones? So UART is from all these protocols we talked about, they're only asynchronous. And therefore, it requires sampling in order to synchronize, to get the data correct and so on. Then if we think about the SPI, yes, it's full duplex. We have send and receive at the same time, and we have a master-slave system. If we compare between UART and the SPI with respect to number of parties on this for the transmission, can we have easily for the SPI for the UART and SPI, or only for one of them, have multiple parties communicating? So multiple in sense of more than two. Can we for SPI and UART have more than two parties easily communicating? Correct. So for SPI we can have multiple parties communicating. For the UART, if we want more than two parties for communication, we need on top some protocol. And then we are similar to I2C. So if we now compare, let's say, UART with I2C, where are there the differences? UART versus I2C, two-wire connection. So UART is half and full duplex. The I2C is usually half duplex. Other differences? I2C is synchronous, so the clock speed can be higher. That is actually this duplex, half duplex, yes? SDA? What do you mean? You mean this one here, because the signal is called SDA. Well, it's just a signal name. So how many parties do you have here versus UART? For I2C, there can be more than two parties, because you have here an address range. So you have a protocol on top. So I2C is kind of not only the transmission, but also the protocol on top. Okay, further questions to that? No, seems to be easy enough. Close this one here, and I go bump. So if we now go to this processor stuff, then I started a little bit with memory. Now, if we consider systems, then usually we distinguish von Neumann and Harvard architectures. What's the difference there? Yeah, exactly. So the difference is we have here for von Neumann, we have one memory for the processor core, and this memory here has data and instructions. That means if you want to load over fixed width bus, you do not want to have this arbitrary large. If you want to load data and instructions, then you would usually first fetch the instruction, then fetch the data. So two operations. In contrast, the von Neumann has this data memory and instruction memory split. So if you want to have effectively two buses to the processor or two connects to the processor, if we want to get data, we can load data and instruction at the same time, which makes the handling more complex, but the speed higher. In modern architectures, usually you have this modified architecture. So you have the caches close to the core, have the splitting to make them as fast as possible, and they load their data from somewhere else, and they load it from a joint memory. And then below, further memory layers are all data and instruction. Okay, yeah, good. Then we looked a little bit into this assembly code, and we discussed what we actually need in order to make this run. And, well, we had this quick sketch of a computer, of a processor. if you look into this, what's the purpose of these, let's call them for the moment just pink bars? What is the purpose of this pink stuff here? What is this? 2? Sorry. Yeah, maybe more specific. Yes, well, to do all the calculation, I need more or less all of this. Maybe I can save some things, yeah, to make it very, very small, but at the end I need all of this for the calculations. But what kind of circuit is this? It's kind of a buffer, it's a register bank. Yeah? So why are there registers between these stages? So effectively, you may hear of pipeline stages in the CPU. So effectively, that's the pipeline stages. So you have one clock cycle, maybe it's longer, yeah, but you have one clock cycle for instruction fetch, then you two have one clock cycle for decoding, then you have one clock cycle for computation, and one clock cycle for write back. Yeah? Now, if you have fetch data, fetch the instruction, and decode the instruction, you can already fetch the next one, right? So it's classical pipelining. Huh? Yes? Yes. That's for this specific architecture.
Okay.
Huh? What you can also see here is that you have a split connect to the instruction set and to the data. Huh? So just as we had this before for the Harvard architecture, you have a split connect to the processor. Huh? Okay. Then the heart of all of this is effectively here this ALU. What is an ALU? Not really? Yeah. Yes? Yes? Yeah. Arithmetic logic unit. So what's the minimum requirement for this ALU? Addition, inversion, and no? So we need to be able to do an AND and an inversion. You can also put this together to an AND gate, because then you have one clock cycle for an AND and one clock cycle you apply to the inputs of the NAND, just both the same, then you have an inversion. Yeah? So you need effectively one NAND gate and one adder circuit, yeah? One full adder, half adder should be sufficient. Then with these few gates you can process effectively everything, whatever task you ever need. Huh? Because the rest is a mapping of that here, and you can just build, for instance, the XOR operation out of inversions and ANDs. You can build an addition out of a 1-bit addition and storage. You can build a subtraction just as an addition, and so on and so forth. So everything, whatever you want to compute, is covered by that. But it's inefficient if you do not have more. That is why we want to have more, either within the ALU or close by. So addition, subtraction, some shift operation, something like this is commonly in the ALU. Something like multiplication, floating point multiplication may come as a separate accelerator. Okay, that's just a drawing of that. And then we had this barrel shifter, which I think there's not much to questions so far. This barrel shifter here. So this barrel shifter at the end, I just redraw this or next to it. Probably a little bit smaller. We make just the decoder. We take two inputs, X0 and X1, and we take here Y0, Y1. Maybe it's better if I exchange the order here, then I have not so many crossovers. So I have effectively two cases. Either I want no shift, or I want shift by, just to be in line, let's say this here is right here, shift by 1. This here is shift by 0. Yeah? So these two cases we have. It's exactly the same what you see here, just that I reduced it to only the lower two and here the lower two. So it's actually this array. Okay. Now what I want to do is, if I have a shift to 0, I want to put this here to that output, this here to that output, right? So I make here a wire, was not good, and here a wire, and here a wire. Nothing yet connected. Okay, now what I want to have is, if x0 goes to y, if we are in this case, we want to establish a connection between here and here, respectively between here and here, right? So we just put a switch here, okay? So, and the switch is connected, or is switched, maybe I dash this a little bit. So the switching is enabled with this blue wire, okay? Now we want to shift, and we do a cyclic shift. Then we open this here. We don't want to have this connection, but we want to connect x0 to x1 and y1, x1 to y0, right? Then they are exchanged, which is the cyclic rotation. So we implement a switch here and a switch here. And this is controlled effectively by this here, and then we need here somehow control the lower one. That's effectively the same what we see here, right? So the only difference between this picture here and that part of this drawing is that here we have now the switches implemented as transistor logic. And this I've drawn last time is just a pass gate. So you have just a transistor pair implementing a switch. That's it. Okay? Good. Then let's go on. And the main topic for today will be the adders, at least for the morning. And I already started on Friday with a bit of the explanation, which you partially also have here on the slides. I just go through this stuff on the slide a little bit step by step, so it hopefully is more clear what I actually want to say here. So we had, just like, let's take this one here. I keep one possibly on the slides. So that I can see that's effectively the same what I draw. Good. We had a quick recap how two's complement works. So do not forget, if you have to write something in two's complement, the first bit gives the sign. Then you can just write it as a binary number, and if you need a negative number, you write a positive number, and then you invert at 1. So if you would try to, let's say, this one here as a negative number, then inverting would give you 1, 1, 0, 1, 1, 1. At 1 would give you 1, 1, 1, 0, 0, 0. And that's actually then negative 8. Good. Then we have said we can write the transform from a binary number into a decimal number as such a sum, where we go over the length of the complete bit string. For us, we only focus on positive numbers. It makes it a little bit simpler for the explanation. For B, the same as for A. And we have for each element, so for instance, let's take this 12. Then the 12 actually is, just to write in the correct form, 2 to the power of 0 times 0 plus 2 to the power of 1 times 0 plus 2 to the power of 2 times 1 plus 2 to the power of 3 times 1 plus 2 to the power of 4 times 0 plus 2 to the power of 5 times 0. That's just a representation from here, right? This here is A0, A1, A2, A3, yeah, and so on. So the A's are just the ones and zeros, the elements we later put into our bit vector. Usually we turn them around, that the least significant bit is on the right. And we have this sum and can do an addition of 12 and 8, either in this space here, or just write it maybe here. The rest is all 0. We can either add in that domain, or we can add in that domain. Either add in that domain here, 12 plus 8 is 20, or we add in that domain, right? We do not change anything. So that's the whole point of what I said here on this slide so far. Okay, now we start with the, let's call it special case, namely with I equals 0. So for I equals 0, we get out here the value 0, 1, or 2, right? If we want to be, or actually for any I, if we want to do a binary, an implementation in hardware, we need to stay in a binary domain. So we can interpret this as we transform A0 plus B0 into 2 times C0 plus, let's call it S0. So all of this here should be in 0, 1. So AI, BI we defined already. C0, S0 is also, I should write the element maybe, should be element of 0 and 1, right? Now what do we do? Well, we draw a truth table. We take A0, B0, C0, S0, and for us, for convenience, I also write here a decimal value. So, which cases do we have? We have 0, 0, 0, 1, 1, 0, 1, 1, and the result should obviously be 0, 1, 1, and 2 in a decimal domain, right? So, now, something unclear? All good? So, now we try to write this here in that form. So, if we want to have a 0 represented as 2 times C0 plus S0, C0 should be 0 and S0 should also be 0, right? If we want to have a 1, then S0 should be 1, C0 should be 0. So, and if we want to have a 2, then C0 should be 1, S0 should be 0, right? Good. Well, what did we construct? This here can be interpreted as we have either A or B. So, this here is A0 X or B0 equals S0. This here is only if the 2 are 1, then we should have a result, output 1. So this is A0 and B0 equals C0. I use this this way with this wedge and V to write logic here, just to not mix it up with digital multiplication and so on. Yeah? Okay, now we can draw this as a circuit, right? If we draw this as a circuit, we have A0, B0. We have the 2 XOR gives the S0, and do this a little bit further down. Adding the 2 together gives C0, right? That's how we would draw this as a logic gates. this is how we would draw the table, the truth table above as logic gates. And this we commonly draw as this symbol called half adder. Is this known? So most likely you heard about that somewhere, probably, hopefully. Somehow familiar or completely? Okay. Okay. Yes. Yes. So I do this with this calculation from the summation, because this will help us later to optimize the structure, to understand why we do things. So, because at the end it always boils down to we want to implement this equation. The computation formula helps us to understand why we do things. So it explains actually why we do this stuff. Yes, yes. Why we can also do specific things in a different way. How we can implement this in a more optimal way. Okay, then we go ahead and we now, we started here from this equation and we have I equals 0. Now, obviously, if we put this here back into our equation, then we come from this equation, I call it star. We have, how to write it, C equals, and then we now have left the sum from I equals 1 to n minus 1 to the power of I, AI plus BI. That's actually what we have here. Just starting, instead of from 0, we start from 1, plus, and then we have 2 times C0 plus S0 for the bit 0, right? Now, I put out the term for 2 power of 1. For all others will be the same, so it's sufficient to make once. So, what we would have is, this is the same as I equals 2 to n minus 1, 2 to the power of I, AI plus BI, plus 2 to the power of 1. And now I put everything which corresponds to 2 to the power of 1, which is A1 plus B1 plus C0, right? So, because C0 is also 2 to the power of 1, right? Can just write a 1 here. So I extracted from the sum here, I extracted from here to here the 2 to the power of 1. I move it back here. So I have 2 to the power of 1, AI plus BI. And I add to this directly the C0. And then I have to add, of course, here plus, I write maybe explicitly 2 to the power of 0, S0. Right? Make sense? So now we have here 3 potential values, namely, or 4 potential values. 0, 1, 2, or 3 can come out. Right? So if we now note this down in a truth table, I again have AI, BI, then we have C, I minus 1. Because if I would now drop out the next, I can fall back to the same equation. So I can do this generally for any I, for I larger than 1. And then we want to have again here Ci and Si, so that this one here is 2Ci plus Si is the meaning, just as before. And we can write a decimal value to that. And then we have 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Yeah? Just classical truth table. So, what should be the decimal value? Here it's 0, 1, 1, 2, 1, 2, 2, 3. Right? Just adding up the bits in a decimal value. interpretation in this binary formula. 0 is obvious 0. A 1 is a 0, 1. A 2 is a 1, 0. And a 3 is a 1, 1. Right? Just interpretation of this equation as a truth table. Okay, now we can look first into this value of Si. Yeah? And now what we can see is if Si is 1, or when is Si 1? Well, it's here, 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 and here. So meaning if we have 1 of the input set or 3 of the input set, an odd number of inputs. Yeah? We can interpret this as Si equals Ai XOR Bi XOR Ci minus 1. Yeah? So if 1 of the bits is set, then we have 1, 0, 0, or 0, 1, 0, or 1, 0, 0, 1. Yeah? Which gives, with an XOR in between, gives a 1. If we have 2 bits set, these two, or these two, or these two, then an XOR of 2 1s always results in a 0, so this gives a 0. If we have 3 1s, this results in a 1. Right? Okay? So, then we do a first straightforward interpretation of when effectively is our, do this calculation here, Ci a 1. This is the case if we have Ai and Bi. Here's also Ai and Bi. There's also 1, so that's fine. Or if we have, where's the next case, Ai and Ci. Yeah? That covers also this one, also fine. Or if we have, where's the last case, this one here, which is Bi and Ci minus 1, right? These are the cases where here is a 1. So this 2 set, these 2 set, or these 2 set, or all 3 set, right? Okay, good. Since these are now with S and C 2 completely split circuit and we can overall do some optimization, we need to transform this a little bit. Yeah? And we start first with writing this down in a little bit longer form. So we have the first term is Ai and Bi, or then I write down this term here as Ai and Bi and Ci minus 1, or Ai and Bi not and Ci minus 1, yeah? Or I take for the right side, we make another equation which is Ai and Bi and Ci minus 1, or Ai bar and Bi and Ci minus 1. Okay? Yes? So we have AIBI, AICI. Yeah? This is effectively AI, CI, BI bar. Right? Is this equation? Or AI, BI, CI, yeah, is this equation. Right? So we just extended effectively this AI and BI, and we have a don't care bit at B. Yeah? AI, BI, CI, we have a don't care bit at B, and this is implemented here with this BI bar. Yeah? So we just split this term so that we extended it to that we can cover these 2 lines also by, so this here is AI and BI bar and CI. This here is AI and bi and ci, right? Minus 1. Yeah. And we have in between an or, which is the same as ai and ci minus 1, which is what we have here. It's just rewriting the stuff to be able to optimize later. Yes, the ci minus 1, this one here, because, well, it depends on how you count. Yeah? By convention, I started here with 0, right? So if I start here with 0, then the output of that was goes here, right? So let me go a step back. So this was the previous one. We have formulated that. That was clear, right? This here has a power of 2, right? 2 to the power of 1. So it's 2 to the power of 1 times bit C0 plus 2 to the power of 0 times bit S0. Yeah? So if I now integrate this in the next step, yeah, I just add it here behind. Yeah? So I have 2 to the power of 1 C0 plus S0, and I have the rest within the brackets here. And then I put out of these brackets here, or out of the sum, the I equals 1. So here we only start from 2, right? And the term for I equals 1 I put here, because I defined this here to be C0. So C0 corresponds to 2 to the power of 1 in my definition, right? Yes, I just collect everything what is 2 to the power of 1. What is multiplied by 2 to the power of 1. And that's A1, B1, C0. That's it, right? Okay. Now maybe for the moment think about here a 1. Then this should be 1, 1, 0, and we want to implement this equation. So it's I minus 1. So 1, 1, 0. Yeah, just because it comes from the previous sum of input coefficients. I'm not sure if this is the best way to count, but at some point you need to decide where you start counting. Okay. Now back to this here, to this transform. Now I remove parts that are already covered, namely by AI and BI here, by this term. We cover already here the first term, right? So this here is can only be 1 if this is already 1. And since there's an or in between, we can just remove this term, right? The same here. The first term is always 1 if this one here is, or can only be 1 if this one here is 1. So we can remove this term if we have the first one, right? So what we are left is, I just write it once explicitly, is AI and BI, or AI and BI bar and CI minus 1, or AI bar and BI and CI minus 1, right? Now I can rewrite this as, this is the same as I have AI and BI, or then I put out here the CI, here's a CI, right? So I can move this out of the equation. I can write is CI, and we have AI and BI bar, or AI bar and BI, right? So what did we do? Well, this is just this here rewritten. Then I put out the CI, or CI minus 1. Should be I minus 1, sorry. So we move out the CI minus 1. Then we have CI minus 1 and AI and BI, or AI bar and BI, so AI and BI bar, or AI bar and BI, right? Just straightforward logic transform. Well, this here effectively is an XOR, right? So we can write this as AI and BI, or CI minus 1 and AI XOR BI. Okay? And this is how we usually write this. So we can now draw a circuit of that. We have the inputs AI and BI XOR together. We have AI, so that's actually this one here, AI and BI ANDed together. Yeah? That is this one here. Then we have an OR gate, and what we OR is effectively AI and BI and AI XOR CI minus 1, right? And this gives CI, right? So this here is a circuit representing that equation. We have AI and BI, that's this one, or CI and AI XOR BI, right? So now we also want to generate the SI. So we have already AI XOR BI that we already have computed. So the only thing we need is we need to compute the result of this here XOR the CI. So we put here another XOR. We connect this here to CI, and this here is SI. Right? So now, with the three inputs, AI, BI, and CI minus 1, we can generate SI and CI. And this is commonly known as a full adder. Okay? So far, okay? Or are there any questions what I should explain? Good? I will scan it and upload it later. Okay. Now we can continue with our formula here. Let's say half a step further. And then we are actually done, because what we have here is we have from here this formula. I can rewrite, let's call this 2 star. We can write this once more as now the sum of I equals 3 to n minus 1 to the power of I, AI plus BI plus 2 power of 2. Then we have here A2 plus B2 plus just from here this CI, so it's C1 plus 2 to the power of 1 times S1 plus 2 to the power of 0 S0. Yeah? Just rewritten what we had before, with now replacing the term A1 plus B1 by 2 to the power of 1 C1 plus 2 to the power of 2 C1 plus 2 to the power of 1 S1. Huh? So we start with this formula. 2 to the power of 0 S0 just stays. Yeah? A1, B1 plus C0 is replaced by 2 times C1 plus S1. Yeah? So 2 times C1 plus S1, plugging it in here. We have 2 times S1, which goes here, right? And 2 times 2, so 2 to the power of 2, times C1, which goes here. Yeah? And what you immediately see is that this here is the same expression as this one here, so it's exactly the same logic. So if we draw this as a circuit, then what we actually did was we took A0 and B0 into a half adder, generated S0 and C0, put this into a full adder, put in A1 and B1, generated C1 and S1, And now if we want to continue this, well, we just put another full adder here, and this full adder here takes A2, B2, generates then S2 and C2, which effectively, this term here corresponds to that full adder. Right? And then we can continue this until at some point we reach some full adder that has as input Cn minus 2, An minus 2, Bn minus 2, minus 1, sorry. This one here is minus 2, the other one are minus 1. And we have here Sn minus 1 and the output Cn minus 1. And since now here is no further additions, that's our most significant bit. So just to keep this in mind, this here corresponds on the input side and on the output side to 2 power of 0, 2 power of 1, 2 power of 3, 2 power of 4, 2 power of, sorry, n minus 1. This here corresponds to 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of n minus 1, 2 to the power of n, because it's 2 times something. Yeah? And the inputs here also correspond to 2 to the power of n minus 1. Here, this here is 2 power of 2, 2 power of 1, power of 1 second, 2 power of 1, this here is 2, this here is 3. So now I'm correct. Huh? Huh? So the inputs all correspond to the same power of 2. Yeah? So 2 power of, what did I do here? 1 second, it should be a 2, sorry. So the inputs all correspond always to the same power of 2. The output S corresponds to the same power of 2 as the inputs. The output C corresponds to 2 times the power of 2 of the inputs. So 1 more. That's the systematic we have. Okay? This construction, you should also still know, is commonly known as Reupload carry adder. And you find it on the slides here. Okay? Okay. A few remarks because we need this later. First remark, if we look into the structure of this Reupload carry adder, of this full adder, then you find here a subcircuit. What is the subcircuit? It's a half adder. So we have here effectively a half adder included in our full adder. That we will use later because we can move all the half adders away to some point and then only focus on this intermediate part. And yes, that's fine for here. Second remark, we have this Reupload carry adder structure here, and I now want to enable subtraction. What would I need to do? So we have this Reupload carry adder structure, and I want to implement with this Reupload carry adder structure, more or less, as close as possible, a subtraction of 2, let's say, stay for positive numbers. What do I need to do? Subtraction. So one option is we implement a second circuit which has dedicated half subtractor, full subtractor circuits. Can be done. I think no one will do this in practice. What if we try to do this with a 2's complement? So we know in 2's complement, if we want to do subtraction, well, we invert one number, add 1, right? And then we add it regularly. So despite the fact that in 2's complement, the most significant entry here has a negative sign, the sum remains completely the same. That's the only difference we have if we go for 2's complement. Meaning this adder here also works for 2's complement numbers. Huh? So, if this here works for 2's complement numbers, and we want to subtract one number from another one, what do we need to do? Well, we do this conversion, subtract, invert, add 1, right? So, I want now to have a structure that allows me to have either addition or subtraction. Then I take here, so this here is only add. Here we have add, subtract. We have our half adder, full adder, and so on, full adder. Yeah. We have our input AI, or let's call it AN minus 1, A1, A0, right? That is 1, and I want to subtract here A minus B. Huh? Or I want to add A plus B. Huh? So, how to implement that I can have a value of B? How to implement that a value of B can be on a control signal, be subtracted or added, so inverted or not. Let's say stay with inverted or not. We can do this with a multiplexer, inverter and multiplexer, or we can do it with an XOR, right? So we have here an XOR, and here an XOR, and here an XOR, and I just connect these with a control signal. Huh? Now this here, you can also do this with a multiplexer. Huh? For a multiplexer, it would be like you have input signal B, you have input signal B inverse, right? And then you switch here for 0, you add, for 1, you subtract. Yeah? So you invert. Yeah? That's the same structure. Now we have B inverted. We need to add 1. What to change to add 1? How to add it? Where? So if you would put here an adder, add 1. I can do a full-blown adder here and add 1. Doubles my area. I don't like this. So what do I do instead? I make a trick. Namely, well, what happens if here in this lowest thing we just add 1? We have there a half adder at the moment, but a half adder cannot take an additional input. So we convert our half adder, we replace this here by a full adder. Yeah? So we have an additional input C I minus 1, C minus 1, right? And we connect it to that point. Done. So what happens now? If we implement here a 0, then for a 0, where is my drawing? Now I lost the correct page here. For a 0 at CI, the AI, BI XOR is just propagated, so that's correct. So it's the same as for the half adder. This AND here blocks, so only the upper part counts. So we have here an AND of AI and BI. The OR gate just propagates the signal, so CI is the same as for the half adder, so we are back at the half adder, right? So if we put the C0, CI minus 1 signal to 0, we have a half adder, just as we wanted for addition. Yeah? We have no inversion, yeah? Because if we have here the 0, then we have no inversion. If we have here the XOR, then for this here being 0, it just propagates, so we have no inversion, right? So we just do an addition. Fine. So addition still works. What happens if we now enable this subtract signal? So if we put this here to 1, if we put this here to 1, in this term here, we can add a 1, right? So we are now able to add here another 1. We have already inverted the signal. We add here a 1, which of course propagates, is automatically, computation is done. Huh? So we have this invert at 1 directly on the fly, just by adding here a few gates in between. And the output here is then, of course, that's missing here, are the sum or difference bits. Yeah? That's why effectively 2's complement is so nice. Yeah? Because you can do such tricks with it. So, invert add 1 is implemented just by having here one full adder, means an OR gate, an AND gate, and an XOR gate on top, and then we can do addition and subtraction with the same circuit. Yeah? And of course, we need here these XORs or this multiplexer structure. So this works for all the adders we discuss, and therefore I do not mention for each adder how subtraction works, because it's just done like here. Yeah? So that you can always just add on top on everything. Yeah? Good. Then I propose a 30 minutes break till 10:50, and then we continue. Sorry for a little delay. Now let's continue. We had this ripple carry adder, and as a last step, we did this with subtraction. Now, this is from a high-level perspective, actually, that is pretty nice, because we have a very modular scheme. If we want to extend this, then we have just to add to the left full adders, and we are done. It is also not super large, also nice. What are drawbacks of the structure? What is the main drawback of such a ripple carry adder? Yes? Why? Yes. So, if we have, or the worst case that can occur is that we have, let's say, for instance, we have, a 1, a -1 at the 1 input, yeah, all ones, and we want to add 1. So, 1, 1, 1, 1, and we add here 1. So 0, 0, 0, 0, 1. What happens is that this here generates a carry. The carry triggers that here a carry is generated. Because before 1 and 0 gives a 0, so there is no carry. If here 1 comes in, here carry is triggered. And so on and so forth, and this carry has to propagate till the very left. So the critical path for this ripple carry adder becomes very long. So, and that's the main drawback. What is the problem with the critical path? It limits our frequency. So we can't run this on a relatively low speed only. What did we learn regarding critical path? What can we do against the critical path? So if your critical path is too long, what can you always do? Split it by, well, you just add a register. And a register will split this critical path into parts. So if I put a register here, then I need 1 clock cycle to compute from here to here, 1 clock cycle to compute from here to here. Doesn't make the overall structure faster, but it allows me to increase the frequency. I can do this together with pipelining. Then I can have the same length. Or I can try to reuse this individual adder stages, that is full adders. And in the extreme case, in the extreme case, you can go for something called serial adder. Effectively, what changes from here to here is where I put the index. Putting the index to a different position should visualize here. We compute over, I call it space. Yeah? So we compute from the full adder to the next full adder to the next one. Here we compute over time. We compute in the first time step the output for the first carry and sum. In the next time step the output for the next carry and the next sum bit, and so on. So we need for n bits to compute, we need n time steps. Yeah? Instead of here having n individual instances. Okay? Makes sense? The rest is exactly the same. And if you draw this over time, then the carry in the next time step means we need a flip-flop. This flip-flop takes the carry out of a full adder and feeds it back as the input into the next time step, right? Yes. So what happens here is you feed in starting with the LSB. That's why, for instance, starting with the LSB is very nice to have. We start here with two registers, two simple shift registers, which shift in each time step one bit towards the full adder. Yeah? The least significant bit is taken here by the full adder. The carry is initialized with 0 upon reset. Yeah? Now, in time step 0, we add A0, B0, generate a carry and a sum bit. We store the sum bit because that's already completed. Yeah? And the carry we have now available for the next time step. In the next time step, we add A1, B1 plus the carry. Yeah? Store the result, the sum bit, here to this register. Feed back the new carry bit into our circuit. In the next time step, we add A2, B2, and the carry, and so on the first, until we have reached the AN minus 1. Yeah? Right. Yes. It's just the same principle as we had for the subtraction. If you apply here 0 as a carry in, so if you apply here a 0 for the carry in, that means the XOR is just a buffer, it's just forwarded. Whatever the input is the output, because 1 XOR 0 is a 1, 0 XOR 0 is a 0, so this is just forwarded. An AND gate, if this is a 0, the output will be always 0. So this part here just vanishes. The upper part, well, the lower here is already 0, so the upper is only propagated. So whatever comes out here is AI and BI, so this is just the half adder that's left if we put this here to 0. So now, why do I put a 0 here in front? Because you need to propagate the last carry out. You could also say, well, I take this here also as always as CN, then I can save this. But if I want to have a dedicated output register, I would just add here 0 and 0 is always 0. So the output here just propagates the carry out. That's, yeah. Because you have then 3 inputs. So effectively, if you look into what we do on a circuit level is, if we put A1 and B1 to 0 here, then we can interpret this as this side here is blocked because there's a 0. Here's at least 1 0, so this here is all 0, right? So the carry is then after the step 0. And AI XOR BI, this here is 0. So whatever is the most significant bit is just the forwarded CI. Okay. So what is the critical path in this one? Exactly. So it depends a little bit on what the delays of your different gates are. But I would say the critical path is defined here from AI or BI through the XOR, through the AND, through the OR. That's the longest path we can identify. Okay? So the critical path effectively in this case is super short. So you can run this at extremely high frequencies. What's the drawback? So one benefit is the high frequency. Another benefit, by the way, is it's super small. It requires 1 full adder, 3 gates here, plus a flip-flop here. So you can hardly get smaller with an adder that can compute an arbitrary number, but there's also a drawback. Well, it's about the number of clock cycles we need. So the latency here is, of course, then n clock cycles to compute this. Well, where do we use the adder usually? In ALU, right? Now assume you have your smartphone whatsoever, and your processor should do a simple operation. It should compute A plus B. What happens virtually all the time. So you want to run your system on your, don't know, gigahertz clock. Yeah? So your Ripple carry adder is probably too slow. Yeah? Applying the Ripple carry adder would have this long critical path, so you decide to go for the serial adder. Now, what happens? Well, your processor loads this into a register, and then your processor that has to run on a gigahertz clock now waits for 32 or 64 whatsoever clock cycles, does nothing than just waiting because your adder requires this time budget to compute the result. That's why it's bad. So, it's not bad in the sense that it's bad for each and every individual architecture, but it's definitely a downside. Okay, now what we can do is we can do a little bit of math. Same equations as before. I just go quickly through it. That's the equation we started with, right? Now, of course, we can split this n minus n bits here. We have a sum with n elements. We can split this in even parts, or into, not even, into equally large parts, right? So you can split a sum into subsums. So we can split into n divided by k parts, each of k bits length. And then we can rewrite the same equation like this. So if here both are 0, then we have 2 to the power of 0. This here is 0, this is 0. If this is a 1, then we have 2 to the power of 1, 0 plus 1. This here is A1, this here is B1. If we are at some point here 1, let's say k is whatsoever 8, then we would increase first here till, till 7. If we are at 7, we would put here, this here to 1. So we have 1 times 8 plus 0 is the next coefficient of the sum. So it's 2 to the power of 8. This here is 8, this here is 8, and so on and so forth. So we have every index here mapped to an index here. It's just written in a more complicated way. Okay? Does it make sense? It's just, this is actual generic here. It's for the Ripple carry adder, yes. But this here is just generic math. Now, what I can do is 2 to the power of I times k plus j. I can write as 2 to the power of I times k plus 2 times 2 to the power of j, right? So effectively the transform I do is that 2 to the power of I times k plus j is the same as 2 to the power of I times k times 2 to the power of j. Yeah? So I can replace this here by that. This here does not depend on j. So 2 to the power of I times k does not depend on j. So I can move it from here inside to the outside. Right? So now I have split effectively in here I have a sum, here I have a sum. This sum runs always multiplies with 2 to the power of j. This here is 2 to the power of I times k. Good. Then I can do the same as before. I can replace this here by carries and sums. That is just what we did before. We replace effectively, let's start with A0. A0 plus B0 as 2 times C0 plus S0. So it's just replacing the stuff, which is what we had before. So then I can, realize again this here with the sum as before with XORs, the carry as before. So sum and carry is defined as before. And what we then have is we have kind of here the output of a Ripple carry adder plus a carry bit that comes out. And then we increment the outer sum, right? So interpreting this as a circuit, just skip this one here. Interpreting this as a circuit gives this here takes k-bit input from some input register They are fed into a ripple carry adder, let's say 8-bit. Can also be another number. This adds up the two numbers and results in a sum bit here plus a carry bit. So we have the sum bit, that is done. The carry bit is fed back into the register. And if we have a ripple carry adder that has as an input a full adder, we can take this carry bit directly into the next ripple carry round and apply exactly the same hardware on the next, let's say, 8 bits or n bits. And we do this again and again until all our data chunks are processed and are ready. So, in other words, you can trade off between a ripple carry adder and a serial adder the latency versus critical path. So I can decide to, let's say we want to process 32 bits. The extreme cases are we have a 32-bit ripple carry adder, or we have a 1-bit, once again, we have a 32-bit ripple carry adder running for 1 clock cycle with long critical path, so low frequency. The other extremum is we have a 1-bit serial adder with very short critical path, high frequency, but we need for 32 bits, 32 clock cycles. Or we can select something in between with this structure. For instance, we say we take a ripple carry adder of 8-bit length. We now need 4 clock cycles for the computation because 32 divided by 8 gives 4. And we have now only a fourth of the critical path length, right? So that's a trade-off we can make. Nevertheless, the overall runtime of this thing is given by the ripple carry adder structure, because we have always this ripple. And also for more advanced adders that we see later, which are faster than a ripple carry adder, we can do the same as for this structure. Good. That was just about the trade-off. Then, questions so far? Then we can go ahead to the next adder structure, which is a carry lookahead adder. Did you come across carry lookahead adders? No? So, before we go into that, we make some definitions because what comes later is is based on these definitions, and we see the similarities best if we do now the definitions first. I just put again our structure here to the front left. Okay, now we differentiate 3 cases. The first one, both inputs are 0. So we interpret now our carry logic, which is effectively we have for a circuit at the output an XOR. We have in front a half adder, and we interpret the result of this half adder as a switching signal for the carry adder, carry chain. So from carry in to carry out. If A1 and B1 are both 0, then this AND gate here blocks, this AND gate here blocks. The carry out will always be 0, right? This is why we call this here a kill. Then we have the case that as well A and B are 1. If both are 1, then here the output is always 1. So we call this just a generate. So that's the lower case here. So if both are 1, this is 1, it's a generate. If only one of them is 1 and the other one is 0, then effectively we block here, we enable this path from input to output, and the output here it depends only on Ci minus 1. So we call this a propagate. So we propagate the carry bit. So we can effectively, we define 3 cases, kill, propagate, and generate. And the carry bit generation can then be written in propagate and generate as the Ci plus 1, so the output of my full adder whatsoever, is a generate or a propagate and Ci. this is exactly the equation we had here, right? Generate or propagate and Ci. Huh? The indexing is a little bit different, but that's just because it's more convenient here to write it like that. To have all the I here on the same thing. Yeah? Okay? So, propagate, generate, we can use, and then we have here maybe another thing. The sum bit effectively is propagate X or Ci. Yeah? That's just, sum bit is the XOR of carry, AI and BI, and that's just the outcome. Yeah? Good. Then, what is the idea of the carry look-ahead adder? Until now, we added 2 bits, generated the carry, added 2 bits and the carry, generated the next, and so on. Why do we have to wait for the carry to be generated for the first bit? We can just directly compute it from all the inputs, right? We can just take all the inputs and generate our carry bit. So, for the first bit, that's first carry, that's trivial. Huh? It's G0 or P0 and Z0. That's just the formula from before, right? For the second stage, so if I look here into this full adder structure, for instance, we look into that point. That's this one here. Then we look into that point. Well, the output can be written as G1 or P1 and G0 or P1 and P0 and Z0. The next one is effectively somewhere here. This carry out, that's the expression from the Reupload carry adder, and replacing here the C2 by that equation, it comes out this here. Okay? So it's just a little bit transforming. Agree that we can do this? Huh? So now, yes, we have a definition of how to come from some input, some generates and propagates to the carry bits. Yeah? This here describes effectively our carry chain. We have an equation that describes how we come from a specific carry bit and a propagate to the sum bit. And we have a definition of how G0 and P0 have to be derived from the inputs. And I go back here. Since G0, G and P have to be derived, and since G is effectively only an AND of 2 inputs, the P is only an XOR, we can here generate or construct, generate, and propagate just with a half adder. So the sum output of a half adder is the propagate, the carry output of a half adder is the generate, right? Good. Then let's build out of this an adder. So we start with a half adder, generate 0, propagate 0. Another half adder is generating G1, P1, generating G2, P2. Then we have a definition how C1 is derived. Note here is the indexing is changed compared to before. So that's maybe a little bit not so good, but it's was more intuitive before to start here with Ci minus 1, and now it's better to start with C0. So we have here the carry from the first stage that is generated by, well, on the previous slide, we had this, here it's also G0 or P0 and Z0. Just applying the logic now to generate and propagate instead of to A and B directly. Then we can, in parallel of computing this, directly compute the carry for the next stage. That was the equation on the previous slide. So we take G1, OR it with P1 and G0, which is this one here, and OR it with, what is it, C0, P0, and P1, right? It's just this equation. Then we take the next logic step. It becomes even longer, but we have the ends here, now 3, 1, 2, 3, and we have an OR gate here to OR G2 with these different terms. Okay? Now we have all our carries, and we have generated these carries fully in parallel, right? So we did not have to wait to compute this carry here until the carry here was computed, right? We did not have to wait with the carry here until this and this one are computed. So it's quicker in a way. Good. Then we need to derive the final sum. And to derive the final sum, well, our construction from a few slides before tells us we have to take the propagate, we have to take the corresponding carry bit, and we have to XOR them. So, propagate, carry, sum bit 0, propagate 1, carry bit 1, sum bit 1, propagate 2, carry bit 2, sum bit 2. There is no propagate 3, so we can take the carry 3 as the most significant bit, right? So, this is, we have now another structure for our adder. That's exactly the same in a different way. What do you identify as benefits and drawbacks? So we have a shorter critical path. The size is increased. So the critical path here is in the worst case through one end and one end, one OR, one XOR, and here this half adder that generates the XOR. So if we draw it like this, it should be faster and it's larger because we need to replicate gates. What do you think if you look into the structure and I look into the AND gate here, the very right AND gate? How many AND gates would you expect for the fourth stage? How many inputs? Yeah. So here it's 4. If we go here, again 4. So we have 2, 3, 4, 5, 6. Is this okay? Not so good, right? Why is it not so good? What means I just explain this with an AND gate because an AND gate is at the end, nothing else than an AND gate with an inverter behind. You remember 3 input NAND gate, right? Somewhere some inputs come in. 4 input, okay, we can do this. 5 input. So in terms of area, probably still more efficient than having separate AND gates. What could be critical? What could be critical from an electrical perspective? I did not hear you. More fault points? You mean because you have more transistors? Well, if you have, let's say you split 1, 2, 3, do another one, then I can talk about 6, and I can easily split in 2. So, if you put this into 2 AND gates, then you have effectively 1 NAND gate with 3, another with the same size, then an inverter for each, probably, depends on how you precisely implement, and then another NAND gate. So more area, more chances to have a fault. No, the most critical thing is, well, in an ideal world, these are ideal switches. In a real world, these are resistive devices, if they are on. So you cannot just stack this, because here, your VDD is fixed, right? Your input here is driven by VDD. At some point, if all those are maybe conducting, you have here still some voltage drops, and you're not longer able with this one here to switch, because your VDS, so the drain source voltage, becomes too low, the share that you have. So effectively, you're limited in what you can build there. And if I have to split this into two, and then build this in a reasonable way so that I maybe only have 3, so 3 to 4 is maybe doable. So if I split this into 2 of 3, then effectively what I have is would have here, let's say we have here only 2 input and AND gates. I have here now increased my critical path again. So the benefit I have effectively from the structure is limited by how many inputs can I build. And that's not too many. Good. So this is just to explain a little bit one problem you have. Another problem you have is, if you remember before, for the ripple carry adder, it looked like this for each stage, right? So maybe we can show this. So the structure here, this one here, we have a half adder, that is this one. We have an XOR, that is effectively this one. And we have here, for the next carry out, an AND and an OR. This is an AND and an OR. It's this one, right? So if I would only draw in this way, I would have a half adder, an XOR, 2 gates. Here the same, half adder, XOR, 2 gates. Half adder, XOR, 2 gates. So not only that the area gets larger, also the wires we need here increase significantly. What means an increased number of wires? If you model a wire as a circuit element, what do you need there? Yes, but which electronic components would you need for the model? Ports. So inputs, outputs, ports means, so now, we want to have a wire. So straightforward, well, we have a wire. On electronic level, does a wire behave like this? No. What you would need? No, sense amplifier would be something here at the input and at the output. So driver or receiver, but no? No? So if you have just a piece of wire, so yes, exactly, this piece of wire, no electronics in here. Exactly, we need a capacitor here actually, and we need a resistor. So usually you have an RC element. You can also split this further and have multiple RC whatsoever, not so important for us. The important point here is more wires is more capacitors. Then each wire here has to drive now, let's take with this G0, has to drive not only the wire here, but it has to drive the wire here, then here the gate, then here the gate, and if I would add further stages, further gates, right? That we commonly call fan out. So the fan out here is relatively large. So we have 2 effects. We have not only a larger area compared to the ripple carry adder, we also have a larger fan out, which means we see the capacity of more wires plus of more gates. So each gate has the input a gate material, right? And this can be seen as a load capacitor for the driver. Meaning, what does a capacitor to our circuit? So let's go back for the wire. If I increase the capacitor here, what does it make to some switching, DC switching? So to DC actually nothing, but if I switch at the input once from 0 to 1, so let's say we have an arbitrary steep edge here, what would receive here? So here you would receive effectively something like that. What happens if I increase the capacitor? Less steep. Less steep. So if you increase the capacitor, you're less steep. What does this mean for our circuit, for the switching behavior? We switch approximately at VDD half. We settle at VDD. This here is time, meaning if our capacitor increases, our circuit gets lower, right? So, long fan or large fan out is difficult because it makes our circuit slow. Large fan in is also not ideal because we need larger gates. Larger gates means we need to increase the size of the transistors. So the size of the width and length of the transistors just to increase the decrease the resistance. We need to limit the number of inputs to a certain extent and so on. So large fan out is also nothing we want to have. So overall, the main points here are we save some time in theory. In practice, we are quite limited because we have this effect of large fan in, large fan out. Okay. Yeah. So fan in is just, I have a circuit. Fan in is, I take a gate and ask how many drivers do I need for this node. So how many wires control this gate. Fan out is, I take a wire or a gate and ask how many other gates do I drive. Fan in is, how many inputs do I have? Fan out is, how many outputs do I have? Okay? Yes. And large fan in, you need here gates that are from design, from the transistor design, larger. Larger gates are typically slower, and you are limited in the number of gates you can actually, and the number of inputs you can actually implement. The fan out says we have additional capacitances, making the circuit overall slower. And these effects limit the benefit of the scale lookup adder so that in practice I would say it's hardly used. In theory, it's a nice idea, and it helps us to understand a little bit the structure here. Namely, we can interpret each and every adder as a layer of half adders that produces, generates, and propagates. A layer for post-processing that usually with XORs generates out of propagates and carry bits a sum bit, and an intermediate structure that is the actual K structure that we try to optimize. Well, now I go back to this a little bit later. Oh no, we do it now. Well, now the critical part is actually the part in between, the generation we need, the post-processing we need. So, in that sense, we can draw here a graph for that. Disclaimer, this one here is a little bit differently implemented, interpreted from what we use later, but I want to have this here to just show the similarity. So, we can draw a graph, pre-processing, post-processing layer, and in between, we have a graph structure giving us the carry logic. So we have one node that takes here, generate, propagate from here, and takes here generates the carry bit. We have one that generates here, generate and propagate, and generates the carry bit, and so on. Each of these things can be interpreted to generate one generate and kind of a propagate again. How this works, we look into detail later. Now, what do we learn from such a graph? Why is this useful? Because we can identify, is this actually an adder later? And we can find specific properties. Namely, what is actually logic depth of our circuit? What is the wiring? Do we need many wires or rather few? We can see what is the fan in, so how many arrows go into one node. We can see what is the fan out, So how many nodes are driven by a single wire? Yeah? In that sense, it helps us to compare structures. The circles effectively interpret such a logic computation. Later it will be a very specific computation, but for now it's just this one here, or this one here, or this one here. And then the output is here some carry. Yeah? In our case, we only need the carry. This GP tuples, I have them because later we have them always. Okay, good. Now we said, well, we want our carry logic. I just removed the post-processing, I removed the pre-processing. Because that we don't care, that's actually we always need it, so no room for optimization. Room for optimization we have here in our carry logic. Now, let's try to reduce the fan-ins and fan-outs here. Yeah? And I start here with this fan-in, which is here an AND gate, driven by this, this, and this. And what you may immediately see is that these three wires here are actually already there. We already computed them. So if we anyway have to split maybe the NAND gate or the AND gate, why not using just this output, right? Because this is something we have already computed. Same here. If we need to split here the gate, these two inputs here are already computed by that. So we can just connect here to here, right? We just do this and see where we end up. Yeah? So we did this. I just need to see if I have something that I don't forget anything. Yeah? So if we compute effectively what this is, then we have now here P and G0, P1 and P0 and C0. Yeah? That's what this OR gate here computes. Now we want to reduce for this OR gate here the fan-in. Then we can try to reduce this equation, and we find that's actually P1 and C1. So effectively, we can reduce here another thing. We can reduce the two inputs here into one input that is driven by an AND gate. And we can do the same here. So this gate here is P2 and G2. This here is P2, P1, G0. This here is P2, P1, P0, C0. We can transform this. Gives this equation, once depending on C1. If I take this equation, that's just C2. So we have P2 and C2. So we can replace all of this by P2 and, where is it? C2, right? So where are we now? I just left the gray part because we need it in a minute. Well, what we have here is AND or C1 fed in into AND or C2 fed in into AND or C3. That's just a ripple carry adder, right? So it's the same structure. It's just this, by this transform, we have now converted it to a ripple carry adder. What might be visible is that sometimes for the carry lookahead adder, we used here an additional AND gate. So there was an AND that was somehow used on top. And thus, we define this here as something we call basic process